Hi friends, so we have come a long way. We are into our ninth week, and the topic is human factors in operation. At the outset, let me tell you, this is one of the very important subject, because here we are talking about safety improvement, risk reduction, and all that. So. Human do a wonderful job. Operators, technicians, they do a wonderful job in managing the safety of the plant, and that's how we have come. Certain industries like nuclear have earned their name for the they got their name for maintaining the highest level of safety and all that. And one of the factor for this is the human factors get a lot of attention in these industries. First lecture will be like I will be introducing the topic, and the second lecture onwards, I have developed a methodology for human reliability, because human, when we talk about it, the human reliability is one of the thrust area of research across the world, because people see a lot of improvements have to be done in spite of having the best record and all that. Why? Because we are dealing with the complex system. Uncertainty associated with understanding human behavior is not like a straightforward thing as we have compared to hardware things actually. Then we will start talking about the human reliability model. This model is called C-cube-B. C-cube-B means 3 C's multiplied, so cube. So that means consciousness, cognition, and conscience. Conscience is the decision of right or wrong. We will see that, and how it is related to human factor. Now, particularly in the present context, we will talk about it. And then we will talk about, in third lecture, consciousness and conscience attributes in CQB. And as and where across the presentation, we will talk about cognition also, because at the end of the day, it is the cognitive capability which drives the human behavior. And then reference human model in CQB, and then we will work upon in the last slide, like crux of the whole four presentation we have, how it is translating into a workable solution. So let us see. Of course, we always draw a parity with the hardware system, and that is how it is. It is a nuclear safety, one of the principle of defense in depth. Because our topmost priority, our safety is an overriding factor. So defense has to be built into the plant design, operation, maintenance, every aspect of safety critical system or risk critical system. And what we mean by defense in depth, that we will understand. So why we are doing it? At the end of the day, it is ensuring the reliability and safety of the plant. That means it should be able to deliver the designated output without interruption. That is for that reliability term, that it takes care of that thing, uninterrupted operation, and at rated power. So then availability factor comes. So like this, and then safety. Safety is, as I mentioned, it is an overriding factor. So it cannot be bypassed. In fact, it's not just a slogan, but there is a document in the plant which is called technical specification, which ensures that various parameters, they are referred as safety limit, limiting condition for operation, and surveillance criteria, training criteria, all designated responsibility. So if we deviate from that document, it becomes a safety case. So it is not that merely talking about safety, it is implementing through documents, and it's like, one of the most, not one of the, technical specification or limiting condition for operation is the LCO. They are basically the document which has to be followed verbatim. So that is the kind of seriousness which is there as far as safety is concerned. Now, we have done our best as far as the designs are concerned, ergonomics, everything. But then finally, it is the humans who are entering. They are looking after the plant operation, maintenance, services, planning, everything. How to transform, and basically we'll come to all those details, but basically they are graduates, and of course you take the best of the lots and then you appoint them, but then they have to be converted, or they have to be transformed into keeping in view the system's requirement. So the training program which orients them to take the responsibility 24/7. Okay, so that means very high level of knowledge has to be interpreted just for the after graduation. Then you enter an organization. You get a general training, or you can say orientation training, keeping in view the requirement of the organization, and then finally you get onto the training on the system itself, which a trainee will be operating in future. And the training period goes from 3 to 4 years, and in exceptional cases it is 2.5 years and all, but not 3 years. So you can imagine the kind of rigorous training they go and qualification procedure they go. So that is how safety critical systems safety is ensured. Okay, and then there has been increasing interest now, and there are some systems that are built because it is a well appreciated fact that the cognitive stress on the operators should be increased. It's not that it is not it is high now. It is that during accident conditions there is a you can say overwhelming parameters, alarms, trips, they come to the control room, and there is a tendency to you get overwhelmed by higher stresses. So why not design the system? So there are inherently safe system, passive features, that means plant will take care of on its own automatically. Even today also, for 30 minutes, let's say this is the median time I'm talking about, the operator, when the accident happen, operator is not supposed to, or is not required to take any action, because the plants are built, or it's the control logic is built in such a manner that the plant remains safe, and after half an hour or 20 minutes or maybe more than that, then we can take the charge, our operator takes the charge and start making the decision, understanding the situation. But then the passive system and inherently safe system, it has got something to do with the material development, thermal hydraulics, control design and all, to a level where it is not minutes, it is hours that the plant takes care of. Plant comes to the safe state, that is shutdown state, and then the safety system automatically they pulled in and ensure the safety of the plant. Okay, but in spite of all those things, we know that there have been accidents. Like in nuclear industry, there were 3 accidents: TMI 1978, Chernobyl 1996, and then 2011 Fukushima. I mean, these accidents were there because sometimes the accidents have a very high impact or adverse impact, I would say, on the society. So and in most of the accidents or most of the sequences, it has been discovered that human factor or organizational factors, they were one of the major contributors. So what we are saying at the end of the, in spite of ensuring doing so many things, the human factor has to be a further focus for operation design. Okay, so this call for a revisit to the existing system, and it's not that I am doing it. Already people are working, the R&D in advanced areas, they are designing different type of inherently safe fuel material, okay, thermal hydraulic processes, defense in depth is being revisited, okay, and things like that. But since today's topic is human factor and we have talked about other things also, we will have in this discussion human factor improvement to the extent possible. Okay, so before I get on to this slide, you can see the Dabbawalas, they reflect a culture of no failure or almost zero failure, because when I say 10 to the power minus 6, one failure in 10 to the power minus 6, that means it is almost they are approaching negligible level or rare event level, and they have done it. They have got the Six Sigma award. Okay, so when the Dabbawalas, when they can demonstrate this level of 10 to the power minus 6 failure, or that means the one opportunity, one failure or two failure in 10 to the power minus 10 to the power 6 opportunities. So this is the kind of demonstration, and the examples are there, and they are basically, it is for everyone to learn about that. You might call their systems are very simple, but no, if you see this job, they are very challenging, and that way it's for everyone to take the lesson. Okay, so when we talk about the human failure, it is not that humans are not good or they don't perform. No, there are millions and billions of opportunities. They have taken the right decision, right actions, but the systems are, as we say, safety critical systems. So safety critical system means system cannot absorb mistakes, especially when a human factor can become a common cause failure. So now I think we have discussed what is common cause failure, one event which is leading to disabling of redundancy, diversity, whatever you may call. Okay, so so this is one thing. So let us make it very clear. Humans have been doing a very good job, but for like any field, anywhere, there is always a scope for improvement. And here also we are looking for what can be done. In all the past situation, the operating staff acted well in time, and whether it is failure or anomalies, and they have corrected the system, and they kept on operating it, and that's why we see nuclear plants have built a record of continuous almost like 3 years of operations and all that. So the examples are there right in front of us. Okay. So then what we can do? We know that human is a complex engineering system, and that complexity is captured or managed by training programs and culture set and all that. But so in spite of that, we want zero. Let us say we want zero accident target. We want to achieve. Okay. So how to do that? And this is one of the important topics, that is human factor. We should work upon it actually. Okay, there are holistic approaches that are based on understanding on human factors and can provide. One of the things I would like to tell here, there are number of human reliability methodologies that are available. But the general observation is that the uncertainty associated with the prediction, it could be a problem of data, it could be a problem of the model itself, anything. But this is a fact, because when you perform the probabilistic risk assessment, you feel that these factors have to be handled. Okay. So what is the way out? As far as the infrastructure, like go on for simulator, go on for digital system in support of training. These are the some of the advanced methods that are available to us, and provide control room with the operator aids, like especially for emergency condition, so that operator, based on the signals that are available to the computerized system, it can present the solution component that is based on the signals. In this system, they are called antecedent, that means trips and alarm approaching the system, and the rules are output are action to be taken. Okay. So these are the things. Then human factor consideration in design. We will talk about operation later on, but the plants are built keeping in view the operational requirement, and that is an inherent component of any design, any good design, or especially the complex engineering system. And this starts right since siting of the and zoning of the systems, because these are mega systems that we are talking about. So if any undesired event happens, it is not only at the plant level, the repercussions are there that might enter into the public domain. So these are the siting and zoning takes care of that, plant is located and its consequences are not there in the public domain. Then one must understand there is an inherent stress associated with the staff. It is 24/7 operation. That means all the 24 hours, 7 days operation plants are operating. So it's not that one person is continuing for all these 24 hours, but still we are going against the biological clock, that is night shift, okay, second shift, and then of course general shift. So this continuously changing scenario, this itself is a subtle cause of differentiation from other jobs. Okay, so and then control room design and console operations. These are the two major operations, and along with this, supervision and surveillance, not only in the control room but through communication mode to all the different areas of the plant. The areas could be from 5 to 15, 20. So getting communication from the area, maintaining it, and then if any deviation is found, the action to be taken, appropriate action to be taken, and all that. So that goes on, and that goes on all through 24 hours. Layout and coordination with the plant areas, just I mentioned, communication also, and then comfort conditions. I mean, some of the areas like control room, we have ground benign condition, that is 22 degrees centigrade temperature and 50% humidity. But this is the ideal requirement for this thing. But all the areas, especially when you visit the equipment and all that, those conditions may not be. So there could be some uneasy situations. So these things should be are taken care, or should be taken care. They are not there because they are also a source of perennial stresses, and that should be managed. Okay. And then in the plant, the maximum, the ecosystem is especially when the shutdown, maintenance management is a very management or coordination intensive job, and the message keeps pouring in from places, and you have to ensure the plant safety also. So you shut down, that's okay, but then still there is a stress on the. I'm not talking about a stress of a high stress, but there is a busy, I would say. The maintenance staff or even operation staff, they are busy so much, so the plant demands the focus, and that focus should be there. Training and qualification system adds. Of course, nowadays it is a digital system, era of digital system, artificial intelligence system. So there should be a thought about having this kind of systems so that the operator feel little not comfortable but confident. Okay, whatever action I am taking it, even my companion operator's aide is also giving me the same advice. So that there is a cross checking. Of course, the operator only takes the decision. They don't operate in the closed loop, because whatever operations have to happen in the closed loop, they go in the form of interlocks. So and then management and support system. These are very, it's a wide area that requires attention, right from human to organization to work areas, management, and then ventilation and ground benign condition. As I mentioned, proper ventilation in the area and ground benign condition in a special area where jobs are required. Why? Because the jobs can be divided into three categories. One is knowledge-based job. Knowledge-based job requires a lot of cognitive load, because it deals with the inference, analysis, logic and rational. Especially a control room ecosystem is basically that we have to do knowledge-based job. Then it is a rule-based job. Control room does rule-based job also, and it does knowledge-based job also. But then other areas also, they require a lot of they have to go back to their memory, see what are the interlock, why this equipment has failed, and why the temperature is increasing, decreasing, and then they have to report back to the control room. So some some rule-based jobs are there even in the skill-based area, and of course skill-based jobs. So normally I would say the complex engineering system, they 90% they remain in the knowledge-based and rule-based domain, and there is a 10% role of skill-based job, like when you operate a switch, if it is going loose compared to our feeling, then you should be able to point out immediately. There was a water in the area, and normally it remains dry. It's a big symptom, or it could be a negligible symptom also, but the report by. So what we come to a conclusion is, all the three jobs, they have their own importance, and the training and management system ecosystem should be designed to cater to these three categories. Okay. Now, typically you would all imagine what is a control room, and also in the open domain I found this. You can see the complexity of the plant. When I am using the word complex, the complexity of the plant, and you would like to see how people are comfortably moving around in the plant during normal operation, because the design is such that they get all the information, and if any small deviation is there, they can pay easily attention. So looking at the so many instrumentation controls and all, one should not get overlapped. They should think how well it is being designed to draw attention even if there is a minor deviation, and the advices, information that are available to them, and in 99.99% time the authorized staff, they take the action and they bring the plant into the control room. Now control room also has been evolving. Generation 1 control room, it was a hardware mimic panel. Mimic panel means how the system engineering drawings are simplified to provide only essential information that is required in support of decision making in the control room environment. Okay. So it will be like flow is which are the system color code, how much is the flow, there are meters and instrumentation, and then their lineup in broad way, it is brought over here, and then we have trips and alarms. That trips means some alarms are combination of alarms that brings the system to shutdown state, or derated state, whatever, or offset state, and then there are some. So we had essentially the generation 1 control room was characterized by wall-based design. Wall-based design means it's one of the very old electronics, which formed in 60s or so, which formed the basis for design of controls. And then we have, and of course along with that there was a relay-based logic. So logic was relay-based operation, and wall was basically what the modern component, we have integrated chips and all that. But if you compare with the walls, the size of the walls and all, you'll get the feel how far we have come in terms of improvement in these systems. And then generation 2 is solid state logic. Solid state logic means electronics. Walls were replaced by solid state logics, and that means they were microchips. But they would have transistors number ranging from 10 to 100 or 150 or not more than that. So that era came in somewhere around 75 or 80s, and this reduced the size of the controls. Okay, and that's how the control room, the generation 2 control room become smarter compared to the generation 1 control room. Generation 3 control rooms are basically digital based technology. Softwares also came into the picture, but let me tell you, many safety critical systems, they are still having a very conservative approach to applying digital system. So even today, there is a fallback arrangement to see that the old hardwired or solid state logic systems they work, because at the end of the day we have to bother about the common cause failure also. Same software sitting in all the 3 channels, and then are redundant channels, and system should not fail. So there are redundant provisions provided, but again the the digital system they came into the existence. Along with that, some operator information system and all. Then generation 4 area came and all that, and control room where visual display logic, multitasking on one screen itself. So depending on the situation, we can have a screen for our use, and then of course main machine interface with advanced hands that system in control rooms as well as in the plant areas. Okay, so so now here we have, in fact, intelligent systems. Directly or indirectly they are entering into the thing, and then they are supporting the operation, and they are based on the like field programmable gate arrays, very advanced chips where systems are designed and all. And then they are normally built where the passive systems are there. So passive system and generation 4, they go hand in hand actually. The availability of national and international code and standards are now available. So control room designs are improving and all. So control room, I would say, is the brain or heart of the plant. And the design of control room to a great extent impact the human factor element. So there is a direct, we call human machine interface. So this is how they are linked actually. Like plants are there, but then the concept of, as I mentioned, main machine interface is always there, and now it is percolating down into the various plant areas also. Okay, so the design of main machine interface system should be such that it moves from presenting the information to giving diagnostic, prognostics, and various state, any deviation in the area, and to ensure that, of course, the principles of ergonomics are very much there, and it helps in design of control room or in the plant areas also, and communication systems are there. So they also finally doubles up for making or reducing the chances of error or anomalies into the for example, the core process goes on in place in the control room is required to plant reliability, while safety systems are located appropriately for transiting. So location of equipment in control room design is which system should be brought to, which indication should be brought to the control room or which not to be brought. It's a very tough exercise, but now we have advanced method like probabilistic risk assessment and all, where we can create an integrated model of the plant, and from there we can pick up importance measure of the plant, and from whatever importance equipments are there, their status can be brought. Earlier the method used to be based on the discussion with the experts and vendors, the direction. Mostly it used to be based on the expert and learning from the past systems. Now, simulators are relatively new entry. In fact, for nuclear power plant, it is there. It has been there for over tens of years. But that now, keeping in view the advantage, it is entering into the system which are not having the risk as of compared to nuclear plant, but other plants like research reactor and all. So this is one example of a simulator system. The availability of simulator has got two main advantage. One, the training efficiency can be increased because the number of sessions that can be performed in the simulator ecosystem cannot be performed in the control room of the plant. And though there are in situ things available, we can observe it and all, and we can learn also hands-on when some operations are going on from the control room. But then the scope of timing and opportunity both increases when we get training on the simulator. Of course, the simulator should be a replica of the plant. So wherever it is not a replica of the plant, some reorientation training should be given before a training goes into the operation directly. So then training is one purpose. Second purpose is, if simulator, of course simulator is a model, it cannot be a plant. So there will be some differences, but then there is an opportunity for a lot of research and development. Some core physics experiments can be performed on this, because these simulators have been built based on the data that is available from the plant. So why not we pay it back or by get the advantage back by doing experiments for checking the, you can call design of experiment, or we can say parametric studies that can be done. So lot of research can be done in this atmosphere, because 90% of the time we will be able to achieve it. We can even simulate many accident conditions in the simulator. So otherwise some of the events will not happen in the life of the plant. Okay, so this is one of the very effective arrangement for training and all that. And of course research also. Typical human factor matrix, I think we'll be talking about it. See, prerequisite is trained and qualified staff. That only can enter as our reference human definition. Then operator experience is one of the thing. Human factor consideration in design, that already we have discussed. Incident, incident, their learning lesson should go to the, and what ecosystem, how much opportunity it provides. It depends on those kind of risk assessment studies should be available to the plant, and it should training should be exposed to that. Insight from human and root cause analysis. Root cause analysis is a very important element. Okay, because every failure, once it has happened, the preliminary analysis does happen everywhere. But then if we understand the root cause of it, we will not be making the changes in that particular where accidents was involved, but we can reflect those insights in many other places where it is required. Contribution to the accidents and all. And then human reliability evaluation program should be part and parcel of this. Statement of risk conscious culture, I would say, is a very important thing, and there should be a way to represent this thing, and there are attributes for this. Okay, so in this lecture we introduced the topic of human factor in general, and it's a context, that is CQB model that we have over here, and the role of training, how it helps in creating the reference model as a first step. Maybe that can be extended to number of years of experience and all that, and that's how we have the and then we have these technical methods to based on the risk-based technologies, we can create a reference model, and idea is same, to reduce the chances of human error by design or by investigation or by root cause analysis or by developing the operator said, whatever it comes. Thank you.